Welcome on the KIN-MATICS channel, my friend. Today we are given a question here. Suppose the second derivative of y plus 4y is equal to x cos of x. Under these conditions, y, in other words, y is a function of x. So they are telling us y evaluated at 0 is equal to 1. Y evaluated at 3 pi over 4 is equal to this. Hence, now after doing that, find y of pi plus y of negative pi. In other words, we are going to first get y of x, then we shall be substituting this to get the answer. Simply, uh, for the homogeneous solution, of course, that's what we start with. Since this is a function of x, as I told you, for homogeneous solution, we equate this part of the function to 0. This is what I'm saying. And we know how to solve it. You just let your y to be exponential of any constant. T is a constant, and x is the variable. So, in other words, t is the constant. So when you get the first derivative, you differentiate this the first time, you get that. Second derivative is this. So I'm going to be substituting these things back. Where the second derivative, which is here, I put that. I don't have the first derivative, but I have y. So by substituting back, you'll be having something of this type, where you can factor it out the exponential tx. However, as you see, this exponential tx can't be equal to 0 for any value. For any real value, it cannot be 0. So the auxiliary equation is this one only. T squared plus 4 is equal to 0 is the auxiliary equation. And by solving it, you find t is equal to plus or minus 2i. However, for t is equal to, remember we said our y, before we started, we said y is equal to tx. So when t is equal to 2i, what happens? When t is equal to I, you shall be having something of like this, which is, if you remember laws of imaginary numbers, here we'll be having cos of 2x plus I sine of 2x. What about when it's negative 2i? You'll be having this. Meaning our homogeneous solution yp is you add a constant c1, then you write the first y you had, plus c2, then this one which we had last. However, when you collect like times, you can really transform this into just a form a cos 2x plus b, where a is that and b is equal to that. Actually, this is the common form. So we are remaining with finding the complementary solution, and we are going to let, because remember, our left side, let me go back to the question. Our question is here. When you look on our left side, it is x cos of x. Because of x, we are going to introduce a linear function, ax plus another constant. If it was x squared, though, I could introduce a quadratic equation, a quadratic expression, maybe ax squared plus bx plus c. If it was x cubed, I could introduce a cube equation. But this is just an x which is power 1, so I'm just going to introduce an equation of a line which is ax plus b. And remember, when you differentiate x, when you differentiate cos, you get sine. Now these things are going to be alternating. That's why I'm saying I'm going to let x plus b, cos of x, then plus b x plus maybe the sine of x, because of cos. Whenever there is cos or sine, you have to let two functions, one for cos and another one for sine. This is what I mean. Let's go back to our solution. We are here. That's why you're simulating it to be ax plus b cos. Then you also for sine with different coefficients. Whenever you have cos, that's what you do. This is the only thing. I think this was the interesting part of it. And if you could figure out this one, everything was so nice. So I'm going to get a first derivative. When you get a first derivative, you have this expression. And also get a second derivative, because we have to substitute this to the original equation. So I have to get the second derivative. And when you get it and you collect like times, this is what you end up with. It may not be visible enough, but I know you can follow up and this is what you'll be having. So now you're going to be substituting back. Remember, we have second derivative plus 4yb equal to that. So you substitute back where there is y, you put it there, and the second derivative. That's what I'm saying, and you simplify to have this expression. So right now we are going to be equating coefficients. This is 3a, which x, cos of x. So you equate it this side, it's a 1. So you have your a at the third, and you try to solve those things. I know you end up, these are the constants you'll be having. A the third says 0, this, that, and b is 0. In other words, when you substitute back those constants, you'll be having your complementary solution appearing to be like this. I think it's amazing because right now, remember, the y is the addition of the homogeneous solution plus the complementary solution, and meaning we had the homogeneous solution is as a cos of 2x plus b sine of 2x, then plus the complementary solution which you have just got, which is here. This is our y. This is what we are struggling to get. Now they gave us some conditions that when you evaluate y at 0, you get 1. So meaning this is a 1, and when x is a 0, this is also cos of 0 is 1, this is a 0, sine of 0 is 1, this is also 0, this is also 0, so you'll be having your a to be 1. What if, and they told us when you evaluate it at 3 pi over 2, you'll be having this. So why is that? And of course we know 3 pi over 2, meaning when you put it here, it will become, it will be 3 pi, this is 3 pi over 4, so when you put here, it will be 3 pi over 2, which is a 0. Sine of 3 pi over 2, it is a negative 1. So this is what you'll be having. You can say b is negative 2 over 9. It is interesting, meaning now the equation we have without the constants is appearing to be like this. Wow, it's amazing. So right now we are just going to substitute the pi. They said, so y of pi plus y of negative pi to be like this. I know when you try to simplify that, you'll be having it as 2. Thanks for watching the video. This is the answer hard to get. Have you liked the video? Please subscribe on the channel for more coming ones. Very interesting.